Hello, today I will be talking about my term project on phase retrieval using denoising diffusion restoration models. And let me first start with the problem definition. This inverse problem is about finding the unknown image X from its noisy Fourier intensity measurements. I used m equal to n setting for uniqueness guarantee up to trivial ambiguities. And this problem is important since the intensity of a Fourier transform of an object is measured in many applications. For example, to view tiny molecular structures, due to the diffraction limit, we should use X-rays, but we can't use lenses for that regime. And one way to solve this problem is coherent diffractive lenses imaging. In traditional imaging, if we eliminate the sample with a uniform plane wave, we get the exact same field in the image plane as the object plane, ignoring the diffraction limit. So this lens creates a perfect image, but in lensless imaging, we get a far field propagated intensity, but this propagation corrupts the field, and we want to back propagate the field to reconstruct the sample, but this field is complex valued. It has both amplitude and phase, whereas we only record its intensity with traditional sensors, so such a lensless imaging application requires phase retrieval. As we also discussed in the class, this far field intensity is proportional to the magnitude of the Fourier transform of the object. This is also true for 2F system with infinite aperture assumption. So we have a support constraint. We have the intensity, which is the squared magnitude of the Fourier transform of the transmission function txy, and we want to find the transmission function using these two constraints. The classical methods solving this problem first guesses an object satisfying the support constraint, then they calculate the Fourier transform of it, and then they enforce the intensity constraint, then they backpropagate it by taking its inverse Fourier transform, and finally they enforce the support constraint. And after repeating these steps over and over again, after many iterations, they get a reconstruction. But as you can see, it's not a good reconstruction. So instead of directly enforcing the support constraint, they also added a feedback function outside the support in the Hayo algorithm. And Hayo algorithm's reconstruction, as you can see, is better. We can interpret this algorithms geometrically. This is like a projection onto convex set methods discussed in the tomography lecture. So we have a set of all functions satisfying the support constraint, and we have a set of all functions satisfying Fourier intensity constraint, and we want to find a solution which is the intersection of these two sets. And error reduction algorithm, ER algorithm, alternatingly enforces these two constraints like this, and geometrically enforcing these constraints corresponds to the projection to that set and finding the closest point in that set. And error reduces in each step, as you can see, but actually we don't get a good reconstruction, and the reason for that is non-convexity of our problem. The previous picture was misleading since the intensity constraint is not convex, and as you can see from this picture, it will stagnate at a local minimum, causing a bad reconstruction quality. And geometrically, instead of projections, Hayo algorithm uses reflections to get better reconstructions. We can also understand this classical methods from an optimization perspective, and we want to minimize this function. And if we apply gradient descent to this problem, we can derive an error reduction algorithm under some assumptions. But if we think of the downsides of the gradient descent, it can stop at a local minimum, and even if the error reduces in each step, it can output a better reconstruction. So classical methods can stop at a local minimum, and reconstruction quality is bad. They can produce many artifacts, and they can amplify the noise. So to get better reconstructions, nowadays researchers use deep learning, and there are many schemes to utilize deep learning for solving inverse problems. The first strategy is end-to-end training. It refers to training a whole network using ground truth and their reconstructions. And the second method is plug and play. It uses deep denoisers to enforce prior knowledge. And the third one, unrolling, unrolls the optimization procedure as deep neural blocks in our deep architecture. But there are many downsides of these current approaches. For example, end-to-end training only works for linear inverse problems like denoising, but it doesn't work for nonlinear non-convex phase retrieval problem, and also it has possible regression to mean issue, which causes blurry smoothed outputs, and it generalizes poorly to other inverse problems if we train it for a specific task. And plug-and-play approaches generalizes well for any task since it uses the same deep denoiser for many various inverse problems, but it possibly has worse speed and performance for specific tasks. And unrolling doesn't generalize as well, and it has also possible regression to mean issue. And none of these approaches generally do not consider the different characteristics of the outputs in different time steps of the reconstruction process, since they utilize the same network in all iterations without providing the step information to the network. And the regression to mean issue can be seen from this diagram. As you can see, if we train our network to minimize the distance metric between ground truth and the reconstructed images, it can cause smoothed blurry outputs. But for good reconstruction quality, a denoiser should output only one of these images, not the average of them, which is shown by blue dot. And this actually shows that a good reconstruction algorithm should be stochastic. It should output multiple images for the same input. So, in contrast to these approaches, by carefully defining a reverse diffusion process with variational inference techniques, diffusion or score-based models have been shown to perform better than other methods for solving inverse problem. And as you all know, generative AI boom is happening right now, and diffusion models are the state-of-art generative models for image creation. And they do this kind of stuff by learning a general image, by learning a natural image probability distribution than by sampling from it. But this probability distribution of natural images, for example, can be quite complex over a very large space, and even if such an underlying distribution exists, we don't know how to express it mathematically or how to fit it. So this is the problem, and the way diffusion models solve this problem is like this. By the way, I will focus on the DPM, diffusion denoising probabilistic models, but there are also many other interpretation of diffusion models like stochastic differential equations or score matching with annealed dynamics, but they all result in similar objectives. I will tell DDPM since I used it in my project. So we define two distributions. One is assumed model Q, and it has no learned parts, and it is just gradual addition of noise. And backward or generative model is parameterized by neural network, and it is gradual denoising process to generate images. Note that we have Markovian assumption for Q, and for learning we use likelihood objective. We take the evidence lower bound over log likelihood, and it is KL divergence between two Gaussians. One is assumed and one is just modeled as Gaussian. And KL divergence between two Gaussians is proportional to their mean differences. After reparameterization trick, we write the iterate at step t like this, and it's ground truth image plus some noise proportional to this. And with further specifications, what they propose as the training objective is predicted noise in xt minus ground truth noise. So they want to predict the noise in the image, and after training this model we go to sampling stage. In order to do sampling, we first start with the random Gaussian noise image, and iteratively we denoise this image. We predict the pristine image with the neural network, and we add some noise, some perturbation to get the next step, and repeat this for a lot of steps in this gradual denoising process. So that was a quick overview of the diffusion model I used, but how can we solve an inverse problem using these diffusion models? That brings us to this paper, DDRM. As opposed to generation of image from nothing, in this case we have an observation y, and we want to condition on it. So one way to do this is defining these generative and assumed models conditioned on y this time, but that definition will depend on a particular inverse problem. Rather, we want to utilize the same diffusion models to solve any linear inverse problem. So they found a way to use a pre-trained DDPM to solve an inverse problem without training it for that particular inverse problem. And here are some of their results for blurring, for downscaling, for inpainting. And to understand what they proposed intuitively, we can first start with the easiest case, noiseless inpainting. So we have a observation y, a masked version of the original image x0, and here h is a diagonal matrix with ones and zeros, and we have no noise in this case. So first we have a random noise, random Gaussian noise, and we use diffusion model to denoise it. But at this stage we didn't use the information of y. And one way to enforce this information of y is simply overwriting the pixels we observed already to get the updated denoise results. This actually corresponds to linear combination. And like DDPM, we combine this with the perturbation noise, previous inputs, to get the next iterant. And we can repeat this to get a less and less noisy image, which is also consistent with y. So mathematically, the overwriting part from our observations can be written like this as a linear combination, and we also have a linear combination like DDPM. And we can just treat the entire thing as a black box, as a linear combination block taking 4 inputs. Now we can focus on more difficult case, noise in painting. So now we have some Gaussian noise in our observation, and to solve this they consider two different scenarios. The first scenario is when the current noise level is at this diffusion model stage is larger than the observation noise, so we are not certain what the image should be, and in this case giving this noisy y actually giving some information even though it's noisy, so we are giving it to our linear combination block as an input. And in the second case, after we have done series of denoising and we have injected some information using the observation, after certain steps we will reach a point where our noise level is relatively small. For example, here given this xt, we are pretty sure what the final image would be, and in this case information about y is too noisy for our use, and it's noisier than the noise level at the next iteration, so it can't help us and we will not use it in this stage. So if my sigma y is larger than my current noise level, I will just ignore my observation and just run DDPM directly, and I will just do unconditional sampling, but otherwise I will use the information coming from y. But in this case y is noisy, and I can't just use like in the noiseless case. Here their idea is to project this output of the diffusion model to noisy samples by adding noise with the same variance with our observation noise sigma y. So our observation has signal coefficient equals 1, noise coefficient sigma y, and our denoise output has also signal coefficient 1, noise coefficient sigma y, and their linear combination has also signal coefficient 1, noise coefficient sigma y. And in this noisy case we also add noise after diffusion model, and this requires different sets of coefficients a prime, b prime, c prime, and to get the desired noise levels they should satisfy these two properties, so we have 1 degree of freedom. As a result, this is their procedure. They use different sets of coefficients for these two different cases, and in their paper they denote them as eta and eta b. And to handle the most general case, any linear inverse problem case, they use SVD. They define y bar and x bar to convert this general linear problem to the in-painting like problem as we discussed. And in this case we have y bar equals x bar plus z. Here multiplication with orthogonal matrix gives the same normal distribution, so since they are all orthogonal matrices, they don't affect the statistics of our problem. And after this transformation in spectral space, we run the mentioned denoising and in-painting algorithm as we discussed. And this is the Q they defined in their paper for a specific H matrix. And here we have 3 cases like we discussed. We have a singular value equals 0 case. We have no information about that pixel in this case, and we have 2 cases where the current noise level is larger or smaller than the observation noise level. And we have linear combination of these elements as the mean of Gaussians. We have our x0, y, and we have xt plus 1. And this is the assumed Q. And this is the learned version of Q. They replace x0s with output of the diffusion model, and they try to learn by minimizing the KL divergence of this learned version of Q with assumed 1. And this is like a variational autoencoder training, like diffusion training. And they prove that under these conditions, the conditional problem and the unconditional problem have the same optimal solution. That means Training diffusion model by defining conditional P and Q for that specific task is the same as using a pre-trained unconditional DDPM model like this. So we don't have to train anything for our specific inverse problem. We can just use the pre-trained DDPM and apply this new sampling procedure, and this is also optimal. And it's also important to note that they use accelerated DDPM by skipping some of the steps by appropriate update rules, and otherwise diffusion models would be very extremely slow. And also they use memory efficient SVD. They do not use matrix multiplication directly. Rather, after analyzing U and V matrices for different H matrices, they use appropriate efficient operations instead, and they mitigate the downsides of the diffusion models with these two details. But in their provided code, the sampling procedure was very different from the paper's one. It was like just end of the file, but they didn't provide or derive this in their paper. They just discussed theoretical stuff, and I tried to derive it for the noiseless case like this. To derive it, I first changed the definitions in the paper to variance preserving ones rather than variance exploding ones, since we use DDPM, which is also a variance preserving model. And after this new definition, I use reparameterization, and after some compact writing using this pseudo-inverse sigma times matrix, I successfully get the compact notation, and using these matrices with some simplifications, I successfully derived their sampling procedure. At a high level, we inject information about y with xt, where we replace the values in the spectral domain with what we know from y, and the sampling process then aggregates xt corrected from y, the current input xt plus 1, it's the noiser output to produce the value for the next iteration. And this is actually corresponds to my intuitive discussion of the paper. It finds some linear combination of these components, and this sampling procedure is written like this. Then I tried to extend it to a nonlinear problem, phase retrieval, by replacing the pseudo-inverse of H with the discussed Hayo algorithm. This is logical, I think, since pseudo-inverse has two important properties, and Hayo algorithm satisfies them. The first property is that taking the pseudo-inverse shouldn't change the measurements, and the second property is that pseudo-inverse h times x should be close to x, since it provides a least squares solution. And yes, these properties are also true for Hayo algorithm. If we compute the Fourier magnitudes of the Hayo output, it also gives the original measurements, and Hayo method also generally preserves the single visual similarity. With this, my developed algorithm is given like this. Note that pseudo-inverse h times y is replaced with a random initialization procedure from another paper, Çağatay Işıl's paper. It runs Hayo algorithm for many random initializations for small number of steps. Then it picks the best one, and it runs Hayo for many steps for that particular one. In my project, I used RGB images instead of grayscale ones, since pre-trained DDPM models expect RGB images, and I think RGB images show the imaging artifacts better. And I applied Hayo algorithm to each channel separately. And also note that Hayo can generate an image with wrong orientation, since such an image also has the same Fourier magnitude measurements. And I calculated PSNR values with respect to the previous iterants to solve this ghost image problem. And I used a simple linear grid search to optimize the hyperparameters of DTRM, but a more optimal procedure would be some gradient-free optimization procedure like genetic algorithms. And here are some of my results. As you can see, it's better than Hayo, but visually and metrically, PSNR values are also better. As you can see, I tried for different parameters, and I observed that hyperparameter selection is very important, since they actually regularize the solution. If eta value is too large, we have low regularization, and the output is still too noisy. It still has some artifacts. And if eta is too small, we have too much regularization and data fidelity is low. And even if we have perfect images without any noise, we produced much more different faces than the ground truth ones, as you can see. So as I said, I tried to optimize these hyperparameters for my problem. And to conclude, diffusion models can act as an efficient prior for phase retrieval problem. And here are my references. Thanks.